The last thing you see before Mars is Earth shrinking behind you, smaller every hour, until the entire planet that made you fits behind your thumbnail. And you still have many months of travel left. That moment alone would break most people. So what really happens during that journey? And here is a question. What song would you want playing the moment you stepped onto the Martian surface? Let me know in the comments. I will pin the most creative answer. Now let's begin. So why has Mars captured the human imagination like almost nothing else? Why is it the one world we keep coming back to, dreaming about, sending robot after robot to explore? Astronomers have been staring at Mars through telescopes for centuries. Back in the 1600s, Galileo turned his crude little telescope toward the night sky and saw a reddish point of light that seemed to move against the stars. He could barely resolve it as a disk. But over the following decades and centuries, as telescopes grew more powerful, something remarkable happened. Mars started to look almost familiar. You could see polar ice caps. You could watch the seasons change. Dark patches would spread and shrink across the surface. In the 1800s, an Italian astronomer named Giovanni Schiaparelli mapped what he called canali, channels, on the Martian surface, and the American astronomer Percival Lowell took that word and ran with it, famously claiming that Mars was crisscrossed with a network of artificial canals built by an ancient dying civilization trying to pump water from the poles to the equator. He was wrong, of course, but the idea lodged itself deep into human culture, and it never really left. We wanted Mars to be inhabited. We wanted it to be alive. Even today, with all we know, there is still a question we have not fully answered, a possibility that has not been ruled out. But we are getting ahead of ourselves. The more practical reason we focus on Mars is simpler and in some ways even more profound. Mars is, by cosmic standards, close to us during what astronomers call opposition. When Earth and Mars are on the same side of the Sun, and at their nearest point, the gap between the two planets can shrink to roughly 34 million miles. That sounds like an enormous distance, and it absolutely is, but compare it to Jupiter, which at its closest is still nearly 370 million miles away, or Neptune, which sits billions of miles out in the dark. Mars is the stepping stone. It is the first real destination beyond the Earth-Moon system that a human being could plausibly reach and survive, and Mars has something else going for it. It has a day that is almost exactly the same length as ours, 24 hours and 37 minutes. It has seasons because, like Earth, its axis is tilted about 25 degrees compared to our 23.5. It has a thin atmosphere, mostly carbon dioxide, but an atmosphere nonetheless. It has a rocky surface you can stand on. It has water, not liquid, not easily accessible, but locked in ice at the poles and bound up in the soil as minerals. It is harsh, frozen, and deeply alien, but of all the places in our solar system, it is the one that feels, at least distantly, like it could be understood, like it could be, one day, a second home. Now, that word, home, that is where things get complicated, because going to Mars is not like moving to a new city, or even a new country. It is not like anything humanity has ever done before. The challenges are so numerous, so varied, and in some cases so deeply strange that even the most experienced astronauts and engineers will tell you honestly, we do not have all the answers yet. What we have are serious plans, bold technology, and a long history of solving problems we once thought were unsolvable. So let us start at the very beginning. Here is something that will immediately reframe everything you think you know about space travel. When we launched the Apollo missions to the Moon back in 1969, the journey took about 3 days. 3 days to travel roughly 239,000 miles. That is already further than most people can instinctively grasp, more than 9 times around the Earth's equator. And yet, in cosmic terms, the Moon is basically right next door. It is so close that we could communicate with astronauts on the surface in real time, with only a 1.25-second delay for the radio signal to travel each way. Mission Control could talk to Neil Armstrong like they were on a slightly laggy phone call. Mars is nothing like that. The distance to Mars changes constantly because both planets are orbiting the Sun at different speeds. Earth takes 365 days to complete one orbit. Mars takes 687 days. So sometimes they are relatively close, and sometimes they are on opposite sides of the Sun, with a gap of more than 250 million miles between them. On average, the distance is around 140 million miles. Now, here is the part that starts to make your head spin. Even traveling at the speed of light, 186,000 miles per second, the absolute cosmic speed limit, a signal from Mars takes somewhere between 3 minutes and 22 minutes to reach Earth, depending on where the two planets are in their orbits. When Perseverance landed on Mars in February of 2021, NASA engineers had to wait 11 minutes just to find out whether the landing had succeeded. 11 minutes of pure silence, not knowing if their spacecraft was safely on the surface or scattered in pieces across the Martian desert. Now imagine you are a human being on that planet, not a robot, not a rover, but a person, and something goes wrong. You radio Earth, you explain the emergency, and then you wait 20 minutes, maybe more, before anyone can even begin to respond. That is the reality of what real-time support looks like on a Mars mission. There is no cavalry, there is no hotline. The crew is, in a very fundamental sense, on their own. To actually get a spacecraft from Earth to Mars using the most fuel-efficient route, a path called a Hohmann transfer orbit, where you essentially arc your spacecraft around the inner edge of the solar system, takes roughly 6 to 9 months. Current estimates for a crewed mission using next-generation propulsion technology hover around 7 months of travel time for each leg of the journey. So you are looking at 7 months to get there, potentially a year and a half or more waiting on the surface for the planets to align correctly for the return window, and then another 7 months to fly back. The total mission duration? Somewhere in the neighborhood of 2.5 to 3 years, 2.5 to 3 years away from Earth, away from everyone you have ever known, farther from home than any human being has ever been. That is the scale of what we are talking about, and it changes absolutely everything. Here is something most people do not realize about interplanetary travel. You cannot just decide one day that you want to go to Mars and launch. The planets do not cooperate on human schedules. To minimize fuel consumption and travel time, mission planners need to wait for what is called a launch window, a specific period when the alignment of Earth and Mars is favorable for a transfer orbit. These windows only open up once every roughly 26 months. Miss the window? You wait another 26 months. That constraint shapes the entire architecture of a Mars mission. It means you have to be ready, completely, utterly, no excuses ready, by the time that window opens. Your spacecraft has to be assembled, fueled and crewed. Your supplies have to be loaded. Your training has to be complete. There is no grace period, no second chance that year. The cosmos runs on its own timetable, and human beings have no choice but to adapt to it. NASA and private space companies like SpaceX have identified the next several favorable launch windows and are planning accordingly. The current generation of Mars mission concepts tends to target the late 2030s and beyond for crewed missions, though SpaceX has stated far more ambitious timelines, with Elon Musk publicly discussing crewed missions potentially as early as the late 2020s using the Starship vehicle, though those timelines have historically shifted. What is certain is that the window will come, and when it does, every second will count. Let us talk about the people for a moment. because this is not just a story about rockets and trajectories and radiation belts. It is a story about human beings, real, fragile, complicated, extraordinary human beings who would volunteer to leave their entire world behind and spend years in the most hostile environment imaginable. The crew of a Mars mission would almost certainly be small. Current mission concepts suggest somewhere between 4 and 6 people, enough to cover the essential skill sets: commander, pilot, flight engineer, medical officer, geologist, possibly a biologist, without requiring so much food, water, and oxygen that the mission becomes logistically impossible. These people would need to be not only technically brilliant, but psychologically robust in ways that are genuinely rare. They would need to function as a team under prolonged stress, isolation, and uncertainty. They would need to make life or death decisions without guidance from Earth. They would need to keep it together when everything inside them might be screaming to panic. History gives us some clues about what that kind of isolation does to people. The studies done on crews wintering over at Antarctic research stations, some of the most isolated environments on Earth, have revealed patterns that mission planners take very seriously. Interpersonal tension builds slowly and then sharply, sleep quality deteriorates, cognitive performance dips. There are what researchers call third-quarter phenomena, a noticeable drop in morale and motivation that hits roughly 3/4 of the way through a long, isolated mission, when the novelty has worn off and the end still feels impossibly far away. On a Mars mission, that third-quarter slump might hit somewhere over the barren, frozen surface of the red planet itself, and the crew would need to push through it. But here is what I find extraordinary about this. Here is the part that fills me with something close to reverence. These people would know all of this going in. They would have read every study, attended every psychological briefing, run every simulation, and they would still raise their hand. They would still look at everything that could go wrong and say yes, because they understand, maybe more deeply than anyone else alive, that this is what humans do. We look at the horizon and we move toward it. We have been doing it for hundreds of thousands of years, ever since the first small bands of our ancestors followed river valleys into unknown territory. The scale has changed, the horizon is different, but the impulse, that beautiful, stubborn, irresistible impulse, is exactly the same. We are, at our course, explorers, and Mars is the next horizon. Now we have covered the why and the who and the basic scale of the challenge, but we have not yet talked about what the actual experience of leaving Earth would feel like. We have not talked about the launch, the controlled explosion that sends a crew into the void. We have not talked about those first terrifying and magnificent hours as the planet you were born on shrinks behind you, the forces involved, the engineering required, the sheer audacity of what a crewed Mars launch actually demands. It is staggering, and there is something happening in the upper atmosphere that most people have never heard of, something that affects every single rocket that has ever left this planet, and it will matter enormously for a Mars mission. Let us set the scene. It is launch day. You have trained for this moment for years, possibly the better part of a decade. You have run simulations until the procedures are burned into your muscle memory. You have said goodbye to your family, knowing that the next time you see their faces in person could be 3 years from now, or never. You have made your peace with that, or at least you have told yourself you have, and now you are lying on your back inside a crew capsule, strapped in so tightly you can barely expand your chest to breathe, listening to the countdown. The rocket beneath you is not just big, it is obscene in its size. To send human beings to Mars, you need a launch vehicle with a level of raw power that dwarfs almost everything ever built. SpaceX's Starship, currently the leading candidate for a crewed Mars architecture, stands roughly 120 meters tall. taller than the Statue of Liberty with its pedestal, taller than the Saturn V that carried Apollo astronauts to the moon. When fully fueled, the entire stack weighs approximately 5,000 metric tons. The super heavy booster at its base generates roughly 74 meganewtons of thrust at liftoff. That is the combined force of approximately 33 Saturn Vs. Numbers like that become almost meaningless without context, so let me give you some. That thrust is roughly equivalent to detonating about 300,000 pounds of TNT every single second, continuously, for several minutes. That is the price of escaping Earth's gravity well, and here is something that might change the way you think about everything that follows. The rocket is not mostly spacecraft, it is mostly fuel. When Starship sits on the launch pad fully loaded, the vast majority of its mass, somewhere around 90 to 95%, is propellant, the actual payload, the crew module, the supplies. The equipment that will support human life for years represents a tiny fraction of the total weight. This is the brutal arithmetic of rocketry, and it has defined spaceflight since the very beginning. To go up, you have to burn down, the countdown reaches zero, the engines ignite, and the sound arrives in your body before it arrives in your ears. It is felt more than heard, a physical pressure that rolls up through the launch pad, through the structure of the rocket, through the seat, through your bones. The thrust-to-weight ratio tips past 1, and for the first time in its life, this machine is doing what it was built to do. Slowly at first, then faster still. The acceleration pushes you back into your seat with a force equivalent to several times your normal body weight. Your face distorts slightly, your vision narrows, breathing takes real effort, everything vibrates. You are leaving the Earth about 60 to 90 seconds after liftoff. The rocket reaches what engineers call max Q. This is the moment of maximum aerodynamic pressure, the point at which the combination of the rocket's increasing speed and the still dense lower atmosphere creates the highest mechanical stress on the vehicle's structure. It is the moment the rocket is most vulnerable to being torn apart by aerodynamic forces alone. You might have noticed, watching rocket launches, that the engines briefly throttle down during this phase. That is completely deliberate. It is a way of easing the stress on the airframe just enough to survive the moment. After max Q, the atmosphere thins rapidly. The sky outside the window shifts from blue to deep indigo to absolute black. The stars appear hard and unblinking, the way they never quite look from the ground. You are crossing into space. The booster burns out and separates, tumbling back toward the landing zone where, in next-generation systems, it will attempt a controlled return, caught, in SpaceX's vision, by enormous mechanical arms on the launch tower itself. That image alone, a booster the size of a skyscraper falling back from the edge of space and being caught like a football, should tell you something about the era of engineering we are living in. It was considered borderline science fiction a decade ago. Now it is a routine part of launch operations. The upper stage engine fires. You are accelerating again, this time toward orbital velocity, roughly 28,000 kilometers per hour, the speed at which you are moving fast enough that as you fall toward Earth, the curve of the planet drops away beneath you at the same rate. You are not escaping gravity. You are falling around the planet perpetually. That is what orbit is. That is what it has always been. But you are not staying in orbit, not for long, because a Mars mission does not simply park in low Earth orbit and call it a day. The orbital phase of a crewed Mars mission is actually one of the most complex and underappreciated parts of the entire operation. In current mission architectures, particularly under SpaceX's Starship concept, the crew vehicle needs to be refueled in orbit before it can make the push toward Mars. That means multiple tanker launches, rendezvous maneuvers, and propellant transfers happening in the vacuum of space before the actual interplanetary burn can take place. Getting the crew off the ground is only the first step. Actually fueling up for the long journey is a separate, enormously complicated operation that happens above the atmosphere, out of sight, away from the cameras. Think about that for a moment. Before your journey to another planet even begins, you are already conducting orbital refueling operations, something no crewed mission in history has ever had to do at this scale. Every day in orbit carries its own risks: micrometeoroids, radiation, mechanical issues, and all of it has to go right before the main engine burn that will kick you out of Earth orbit entirely and send you on a trajectory toward a world that is, right now, tens of millions of miles away. When that burn finally happens, when the engines fire for the last time in Earth's gravitational neighborhood and the telemetry confirms that your trajectory is set, something shifts that is hard to describe. It is not dramatic. There is no siren, no flashing light, no announcement over a loudspeaker. The engines cut off, the vibration stops. The silence of deep space settles in around you like something heavy and soft at the same time. And Earth, for the first time, begins to shrink, not the way it shrank during launch, when you were still close enough to see coastlines and cloud systems and the deep familiar blue of the oceans. This is different. Over the hours and days following the departure burn, the planet that made you, the only world your species has ever known, the pale blue dot that Carl Sagan described with such devastating accuracy, becomes something smaller, something fragile-looking, something you want to protect without quite knowing how. Astronauts returning from the International Space Station have described what is called the overview effect, a profound, almost spiritual shift in perspective that comes from seeing Earth from space. The borders disappear, the arguments seem small, the beauty is almost unbearable. Now imagine that feeling but multiplied, because you are not in low Earth orbit, where the planet still fills a third of your sky. You are leaving, really leaving, and every hour, every day, that blue light behind you grows a little dimmer. By the time you are a few weeks out, Earth and the Moon are visible together as a pair, one bright, one dim, against the star field. A few weeks after that, Earth is just another point of light. Beautiful, yes. Unmistakable, yes. But a point of light nonetheless. You are now, by any measure that matters, alone in deep space. And this is where things get genuinely difficult. Not because of anything dramatic, not because of an explosion or a collision or a systems failure, though all of those are real risks we will get to, but because of something quieter and in some ways more insidious, something that no amount of engineering can fully solve. The human mind was not built for this. Our brains evolved on the African savanna, tuned to a world of seasons and social groups and horizons we could walk toward. We are creatures of place, of belonging, of connection, and out here in the dark between worlds, all of that is gone. The psychological research on long-duration spaceflight is sobering. Studies conducted on ISS crews, on Antarctic winter-over teams, on submarine crews, all of them show that prolonged isolation and confinement produce predictable, measurable effects on human cognition and emotion. Attention narrows, irritability increases, the ability to read other people's emotions, a skill we usually take completely for granted, actually degrades. Sleep becomes difficult and fragmented, and then there is the communication delay to deal with. By the time you are a few months out from Earth, messages to your family take 10, 15, 20 minutes to arrive. A conversation becomes an exchange of letters, each one arriving long after the moment it was written. You cannot call home. You cannot hear a familiar voice and have it respond in real time. You are separated not just by distance but by time. NASA and other space agencies have been studying this problem seriously for decades, and they have made real progress. Crew selection processes now include intensive psychological screening. Mission architectures include private communication spaces, personal time, carefully designed work and rest schedules, There are plans for virtual reality environments that let crew members escape mentally, even briefly, to somewhere familiar, a forest, a beach, a living room. None of it is a perfect solution, but all of it is the result of hard-won knowledge, built slowly and carefully by researchers who understand that the most fragile component on a Mars mission is not the heat shield or the life support system. It is the human being. And speaking of things that threaten the human being, we have not yet talked about the single greatest physical danger of the entire journey. The thing that keeps mission planners up at night more than almost anything else. The thing that is invisible, odorless, completely silent, and passes through the walls of your spacecraft like they are not there. We are talking about radiation. And we are going to go deep on this soon, because what the science actually says about radiation exposure on a Mars mission is both more terrifying and more fascinating than most people realize. There are particles out there in interplanetary space that were fired from exploding stars thousands of light years away, and they are heading toward your spacecraft right now. There is also something called a solar particle event that can deliver a lethal dose of radiation in a matter of hours with almost no warning. And then there is the question of what happens to the human body, specifically the brain, after months of continuous exposure to the cosmic radiation environment. The answers are uncomfortable, but they are also the frontier of some of the most exciting biology and physics being done anywhere on Earth right now. And you need to know about it. Let us talk about something that you cannot see, cannot feel, cannot smell, and cannot hear. Something that is passing through your body right now as you watch this, sitting wherever you are. It is passing through the walls around you, through the ceiling above you, through every cell in your body. Most of the time on Earth, it is at a low enough level that your body handles it without complaint. Your DNA gets nicked and damaged constantly by background radiation, and your cellular repair mechanisms fix it, quietly and efficiently, billions of times over the course of your life. You never notice, you never feel it. It is just part of being alive on this planet. But leave Earth, and everything changes. Our planet is wrapped in two invisible shields that most people have never really thought about. The first is the magnetosphere, a vast, dynamic bubble of magnetic field generated by the churning molten iron in Earth's outer core. It extends tens of thousands of kilometers out into space in all directions, deflecting the constant stream of charged particles pouring off the sun. Without it, the solar wind would gradually strip away our atmosphere, the way it stripped away Mars's atmosphere billions of years ago. Mars lost its magnetic field early in its history, and the consequences were catastrophic and permanent. The second shield is the atmosphere itself, roughly equivalent in radiation protection to about 10 meters of water sitting above your head at all times. Together, these two layers reduce the radiation environment at Earth's surface to something manageable. The moment you leave low Earth orbit, both shields are gone. Out in interplanetary space, between Earth and Mars, you are exposed to two distinct sources of radiation that present very different kinds of danger. The first is solar energetic particles, high-speed charged particles, mostly protons, ejected from the sun during solar flares and coronal mass ejections. These events can be partially predicted, and missions include monitoring systems to give some warning. But the window between detection and impact can be as short as a few hours, and the doses delivered during a major solar particle event can be enormous, potentially life-threatening within a matter of hours if the crew is not behind sufficient shielding. The Apollo astronauts got lucky. During the Apollo era, several major solar particle events occurred, but none of them happened to coincide with a mission in progress. The Apollo 16 crew, for example, was between missions when a large event struck. Had they been in transit, exposed and unprotected, the outcome could have been very different. On a 7-month journey to Mars, the probability of encountering at least one significant solar particle event climbs dramatically. Mission architects know this, and spacecraft designs include what is essentially a storm shelter, a small, heavily shielded compartment where the crew can retreat during an event. It is cramped, uncomfortable, and possibly requires days of confinement, but it could save their lives. The second source of radiation is in some ways even harder to deal with because there is no warning system and no real way to predict it. These are galactic cosmic rays, and the name alone should give you a sense of how far they have traveled to reach you. These are not particles from our Sun. They are atomic nuclei, stripped of their electrons, accelerated to near-light speed by some of the most violent events in the universe. Supernovae, neutron star collisions, the jets of active black holes, and then flung across the galaxy over millions of years, until they happen to intersect the tiny patch of space your spacecraft is occupying. When a high-energy galactic cosmic ray hits your spacecraft wall, it does not simply stop. It creates a cascade of secondary particles, a shower of radiation that in some cases is actually worse than the original particle. Heavier shielding can make this problem worse, not better. For certain types of particles, NASA researchers studying this problem have done some extraordinary work over the past 2 decades. Data from the Curiosity rover's radiation assessment detector, which measured the radiation environment both during its 8-month cruise to Mars in 2012 and on the Martian surface, gave scientists their first detailed measurements of what a real interplanetary journey looks like in terms of radiation exposure. The numbers were significant. During the cruise phase alone, Curiosity's instruments recorded radiation doses equivalent to roughly 100 milligray of charged particles, more than an astronaut would receive during 6 months on the International Space Station. And on the surface of Mars, without Earth's magnetic field and with only a thin sliver of atmosphere for protection, the daily radiation dose is several times higher than what ISS crew members experience. Cumulative estimates for a complete Mars mission, transit, surface stay, return, suggest total radiation exposures that push against, and in some scenarios exceed, the career limits currently set by space agencies for astronaut radiation exposure. Those limits are not arbitrary numbers. They are based on statistical models of lifetime cancer risk, and exceeding them meaningfully increases the probability that a crew member will develop radiation-induced cancer years or decades after returning home. But here is where the science gets even more interesting and more troubling. Cancer risk, as serious as it is, may not even be the most immediate concern. Research published in the last several years has pointed to something that nobody anticipated quite as clearly: the effect of cosmic radiation on the brain itself. Studies conducted on rodents exposed to simulated galactic cosmic ray environments have shown measurable changes in cognitive function, specifically in areas related to memory, decision-making, and anxiety. The animals showed increased anxiety-like behavior, reduced performance on memory tasks, and structural changes in certain brain regions. The particles were literally altering the neural architecture. Now, rodent studies do not automatically translate to human outcomes, and researchers are careful about overstating these findings. But the underlying physics is not in question. Heavy ion cosmic ray particles, the kind that dominate the deep space radiation environment, are particularly effective at causing complex, clustered damage to DNA and neural tissue, the kind of damage that cellular repair mechanisms struggle to fix cleanly. The implications for a crew that needs to be sharp, focused, and cognitively intact through a 7-month transit, a surface mission, and another 7-month return, that is a question that researchers are working on with urgency. The solutions being explored are genuinely fascinating. One approach involves pharmaceutical interventions, antioxidant compounds and other drugs that may help cells repair radiation damage more effectively. Research into drugs originally developed for cancer treatment has shown some early promise in this direction. Another approach involves materials science, developing new shielding materials that are more effective against heavy ions without generating as many secondary particles. Hydrogen-rich materials are particularly promising because hydrogen nuclei are light enough that they absorb and scatter cosmic rays without producing as destructive a secondary shower. Polyethylene, water, and certain plastics rank among the best passive shielding materials currently available. Some mission designs incorporate the spacecraft's water supply as part of the shielding around the crew's sleeping quarters, a practical and elegant solution that serves double duty. There is also a more radical idea that has gained serious traction in recent years. What if you simply made the journey faster? The longer you spend in interplanetary space, the more radiation you accumulate. Reduce the transit time from 7 months to, say, 3 months, and you cut the exposure nearly in half. This is one of the driving arguments behind the development of advanced propulsion technologies, nuclear thermal propulsion, nuclear electric propulsion, and further out, concepts like nuclear pulse propulsion or even fusion drives. NASA's Space Nuclear Propulsion Program has been actively funded and researched, and nuclear thermal rocket designs could potentially cut Mars transit times significantly compared to conventional chemical propulsion. The physics is well understood. The engineering challenges are enormous but not insurmountable. The political and regulatory landscape around launching nuclear material into space is complex. But the conversation is happening, and it is serious. And there is something poetic about this if you step back and look at it from a distance. The same nuclear physics that was first harnessed in the 1940s for the most destructive purposes imaginable, the same fundamental force that powers the stars, that forges the heavy elements in supernova explosions, could be what ultimately gets human beings to Mars safely. The universe's most violent processes redirected into something that carries life across the void. There is a kind of cosmic irony in that, a kind of hope, but let us say the radiation problem is managed. Let us say the shielding is adequate, the solar particle events are weathered, the pharmaceutical protocols are effective, and the crew arrives at Mars with their cognitive function intact and their cancer risk within acceptable bounds. That is not the end of the physical challenges, not by a long stretch, because while the radiation has been quietly working on their DNA this entire time, something else has been happening to their bodies, something slower, more visible, and in its own way just as alarming. Their bones have been dissolving, not dramatically, not catastrophically, but steadily, measurably, in a way that begins within the first few days of weightlessness and continues relentlessly for as long as they remain in microgravity. The human skeleton evolved under the constant pull of Earth's gravity. Every step you take sends a tiny mechanical signal through your bones, a signal that tells your bone-building cells to stay active, to keep depositing new material, to maintain the density and strength that lets you walk and run and carry things. Remove that signal and the bone-building cells slow down while the bone-resorbing cells keep working. The net result is bone loss at a rate of roughly 1 to 2% per month in the most affected regions, the hips, the spine, the femur. 6 months of weightlessness can leave an astronaut with bone density equivalent to someone decades older, and that matters enormously for what comes next. Because at the end of a 7-month transit in microgravity, this crew is going to have to land on Mars. They are going to have to stand up under Martian gravity, about 38% of Earth's, and function. They are going to have to work, move equipment, conduct science, potentially respond to emergencies. With bones that have been weakening for the better part of a year, the countermeasures developed on the ISS, rigorous daily exercise protocols, resistive loading devices, pharmaceutical interventions, help significantly. Astronauts who follow the full exercise regimen on the station lose substantially less bone than those who do not. But the exercise equipment takes up space and mass in the spacecraft, and no matter how diligently the crew trains, some degradation is essentially unavoidable on a journey this long. Muscle mass follows a similar trajectory. Cardiovascular fitness declines. The fluid redistribution that happens in weightlessness, fluids shift toward the head, causing facial puffiness and increased intracranial pressure, may have long-term effects on vision that researchers are still working to fully understand. Scott Kelly, who spent nearly a full year aboard the ISS in 2015 and 2016, as part of NASA's twin study with his identical twin brother Mark, provided an extraordinary window into what prolonged spaceflight does to the human body. His telomere dynamics changed. His gene expression shifted in ways that were measurable and surprising. His cognitive performance showed subtle changes compared to his ground-based twin. Most of these changes reversed after he returned to Earth, but not all of them, and not immediately. And Kelly spent his year in low Earth orbit, with Earth's magnetic field still partially protecting him, with resupply missions arriving regularly, with the option to return home in an emergency within hours. A Mars crew has none of those safety nets. This is not meant to be frightening, or at least not only frightening, it is meant to give you a genuine sense of what these people would be taking on, what they would be knowingly, willingly subjecting their bodies and minds to in the service of something they believe is worth it. And the reason I think it is worth dwelling on is this. Every single one of these challenges is being worked on right now, not in some distant theoretical future, but today by researchers at NASA's Human Research Program, at universities, at private aerospace companies, at international space agencies around the world. The problems are real, and the people working on them are real, and the progress is real. Science is not a destination. It is a process, and the process is moving. But here is what I have not told you yet. Here is the thing about the journey to Mars that does not get nearly enough attention. Once you have survived the radiation, managed the bone loss, held the crew together psychologically, and navigated 7 months of empty space, you still have to actually land. And landing on Mars, it turns out, is one of the most technically demanding feats in all of aerospace engineering. It is so difficult that engineers gave it a nickname that tells you everything you need to know. They call it the 7 minutes of terror. We are going to go through every single second of it. From the moment the spacecraft hits the top of the Martian atmosphere to the moment, if everything has gone right, the landing legs touch the ground. What happens during those 7 minutes is a masterpiece of physics and engineering and controlled desperation, and understanding it will make you see the Perseverance landing, and every Mars landing before it, in a completely different light. Stay with me. This is where we fall. 7 months. You have been floating in this metal shell for 7 months. You have watched Earth shrink to a pale dot behind you. You have done your exercises, taken your medication, eaten your carefully rationed food, had your arguments and your moments of laughter and your long stretches of silence. You have watched Mars grow slowly in the windows, first a faint reddish smudge, then a disk, then a world, a real, detailed, textured world with dust storms and polar caps and ancient canyon systems so vast they would stretch across an entire continent back home. And now, in a matter of hours, you are going to try to land on it. The approach phase begins days before the actual entry. The crew and mission control, communicating with that maddening delay that by now has stretched to somewhere around 20 minutes each way, have been refining the trajectory constantly, making small corrective burns to line up the spacecraft with its entry corridor. That corridor is narrow, terrifyingly narrow. Enter the atmosphere at too shallow an angle, and you skip off the top of it like a stone off water, bouncing back into space with no second chance. Enter too steeply, and the heat generated by atmospheric compression overwhelms your heat shield in seconds. The window between those two outcomes is measured in fractions of a degree, and then there is the atmosphere itself. Because here is the thing about Mars that makes landing there so uniquely, almost perversely difficult. The Martian atmosphere is roughly 1% the density of Earth's. 1%. It is thin enough that it is essentially useless for slowing you down the way Earth's atmosphere slows down returning spacecraft. But it is just thick enough, just barely, maddeningly thick enough, that it generates enormous heat during entry, heat that would destroy an unprotected spacecraft in seconds, so you get all of the heat and almost none of the braking. You arrive at the top of the Martian atmosphere, traveling at roughly 20,000 kilometers per hour, and you have to slow to nearly zero before you hit the ground. A ground that in many of the most scientifically interesting landing sites sits at low elevation, meaning you have even less atmosphere above it to work with. This is the problem that has humbled engineers for decades. It is the reason that landing anything significant on Mars is so brutally difficult. It is the reason that of all the missions ever sent to Mars, from the Soviet attempts in the early 1970s through the American Vikings, Pathfinder, the two Mars exploration rovers, Phoenix, Curiosity, and Perseverance, a significant fraction simply failed, crashed, disappeared. The planet swallowed them without ceremony. For a crewed mission, the stakes are different in a way that does not need explaining. The entry, descent, and landing sequence, what engineers call EDL, begins when the spacecraft first bites into the upper wisps of the Martian atmosphere. The vehicle is oriented with its heat shield facing forward, and almost immediately the plasma begins to build. The atmospheric compression in front of the spacecraft heats the surrounding gas to temperatures hotter than the surface of the Sun, somewhere in the range of thousands of degrees. The heat shield absorbs and radiates this energy, protecting the vehicle behind it. From inside, the crew cannot see anything. The plasma sheath that forms around the spacecraft during entry blocks all radio communication. For several minutes they are completely cut off, not just from Earth, but from any signal at all. They are inside a fireball, traveling at hypersonic speed, through an alien sky, and there is absolutely nothing they can do but wait. This communication blackout is one of the reasons the sequence is automated. No human pilot is fast enough to react to the changes happening during EDL. The onboard computers are making decisions hundreds of times per second, adjusting the vehicle's orientation, managing the heat load, preparing for the next phase. The crew are passengers, extraordinarily trained, deeply knowledgeable passengers, but passengers nonetheless, strapped in and trusting the engineering. As the vehicle decelerates through the atmosphere, the heat shield does its job and the plasma fades. But the spacecraft is still moving far too fast for any landing system to handle. On smaller Mars missions, the rovers, engineers have used enormous parachutes at this stage, deploying them supersonically to help shed speed. But here is where the crewed mission faces a problem that has no clean solution from past experience. The parachutes that worked for Curiosity and Perseverance, which weighed roughly 1 metric ton each, are nowhere near sufficient for a crewed spacecraft that could weigh dozens or even hundreds of metric tons. Scaling up parachute systems to handle that kind of mass in Mars's thin atmosphere runs into fundamental physical limits. The parachutes would need to be so large and the deployment forces so violent that the engineering becomes almost impossibly complex. SpaceX's answer to this problem with Starship is characteristically bold. Rather than relying primarily on parachutes, The plan involves using the engines themselves to slow the vehicle, a technique called supersonic retropropulsion. The engines fire against the direction of travel while the spacecraft is still moving at supersonic speeds, pushing back against the velocity with raw thrust. This has been demonstrated in Earth's atmosphere during the Falcon 9 booster landings, which you have probably seen in those now iconic videos of rockets descending tail first and touching down on landing legs. But doing it in Mars's thin atmosphere at the scale of a vehicle as massive as Starship is an entirely different engineering challenge. The engines have to fire reliably, precisely, and powerfully enough in an environment where the atmospheric pressure is 1/100th of what they were tested in. NASA's own crude Mars lander concepts involve variations on this theme, combinations of aerodynamic deceleration, possibly inflatable heat shield technology, and powered descent. The inflatable decelerator approach is fascinating. The idea is to deploy a large, lightweight inflatable structure around the spacecraft during entry, dramatically increasing the aerodynamic drag surface without adding the weight penalty of a rigid heat shield of the same size. NASA has been testing this technology under a program called LOFTID, the Low Earth Orbit Flight Test of an inflatable decelerator, and the results have been genuinely promising. But let us bring this back to the human experience. Because while the engineers are solving the physics, let us think about what it feels like to be inside that vehicle. The deceleration forces during entry are intense. Depending on the entry profile, crew members could experience several times their body weight pressing down on them, not quite as severe as the most aggressive fighter jet maneuvers, but sustained, relentless, and combined with everything their bodies have already been through. Bones that have lost density over 7 months of weightlessness are now being loaded again, suddenly, for the first time since Earth. Muscles that have atrophied despite the best exercise protocols are being asked to perform. The vestibular system, the inner ear apparatus that gives you your sense of balance and orientation, has been floating in microgravity for 7 months, and now it is being asked to make sense of gravity again, of acceleration, of up and down. There are very real concerns about whether a crew could physically respond to an emergency during the EDL sequence. If something went wrong, if the computers needed human input, if a manual override was required, could they do it? Could they think clearly, move their limbs purposefully, read instruments and make decisions while their bodies are being hammered and their inner ears are screaming confusion after months of weightlessness? This is not a hypothetical worry. It is an active area of research, and the answers have direct implications for how crewed entry and landing procedures are designed. One proposed solution is to conduct the most demanding parts of the surface operations after a recovery period, to land, seal the habitat, and then give the crew several days to readapt before asking them to do anything physically strenuous. That is reasonable and probably necessary. But emergencies, by their nature, do not respect recovery schedules. Now, let us say the deceleration goes as planned. The speed is dropping, the atmosphere is doing its small share of the work, the engines are firing, the vehicle is oriented correctly, the onboard systems are all nominal. In the final seconds, the landing legs extend, massive, engineered structures designed to absorb the remaining velocity and stabilize the spacecraft on whatever terrain the landing site presents. And then something happens that is almost impossible to describe adequately. The engines cut off, the dust which has been blasted outward by the engine plume begins to settle, the vibration stops, the noise disappears, and in the sudden extraordinary silence, 7 months of travel, hundreds of millions of miles of void, all that radiation and bone loss and psychological strain and technical complexity, all of it resolves into a single crystalline moment. The spacecraft is on Mars, not a robot, not a rover, A vehicle carrying human beings is sitting on the surface of another planet. For a moment, nobody moves, nobody speaks. The instruments are reporting, the computers are running their post-landing checks, and somewhere in the back of everyone's mind is the understanding that they have just done something that no human being has ever done in the entire 4 billion-year history of life on Earth. They have carried living minds to another world, and then someone laughs, or cries, or both at the same time, because that is what humans do when the impossible becomes real. But here is the thing, and this is important. Landing is not the end. It is not even close to the end. It is, in a very real sense, just the beginning of a completely different set of challenges. Because now they are on Mars, and Mars is trying to kill them in several entirely new ways. The habitat has to be set up, the life support systems have to be checked and verified. Food and water and oxygen have to be managed with a precision that allows zero margin for error. Dust, fine, pervasive, chemically reactive Martian dust, is going to try to get into everything. The suits have to work perfectly every single time because one failure during an EVA, an extravehicular activity, a walk outside on the Martian surface, could be fatal within minutes. And the science, the actual reason they came, the search for answers to questions that humanity has been asking since we first turned our eyes toward that reddish wandering light in the ancient sky. The science has to happen somehow. In the middle of all of this, what is it actually like to stand on the surface of Mars? What does it look like, sound like, feel like? What would you see when you look up at the sky? What would the sunsets be like? Would you feel the wind? And then, the question underneath all the other questions, the one that has been there all along, the one that drove every mission and every telescope observation and every late night in every laboratory, is there or was there ever any sign of life? That is what we will talk about. The surface, the science, the search, and the answers we already have that are far stranger and more tantalizing than most people realize. You are not going to want to miss this one. The hatch opens, that is how it happens. Not with a grand ceremony, not with a countdown or a fanfare. After all the checklists have been completed, after the suit pressure has been verified, after the airlock has cycled and the internal pressure has equalized with the near vacuum outside, someone reaches out and turns a handle, and the door swings open onto another world. The first thing you notice is the light. It is not what you expected. You expected darkness maybe, or the harsh, bleached light of space. But Mars has a sky, and that sky is doing something strange and beautiful. It is not blue. It is not black. It is a pale, dusty, butterscotch color, somewhere between tan and salmon and the faint orange of a hazy autumn afternoon back home. The fine iron oxide dust suspended in the thin Martian atmosphere scatters light differently than Earth's atmosphere does, and the result is this otherworldly amber glow that hangs over everything. On a clear day, the sun is visible, smaller than it looks from Earth. Since Mars sits about 50% farther from it, a sharp white point that you absolutely cannot look at directly, surrounded by that warm, dusty halo. At sunset, something even stranger happens. The colors invert. While sunsets on Earth burn red and orange and gold, the Martian sunset glows blue. The same dust that makes the daytime sky look orange scatters the shorter blue wavelengths of light efficiently when the sun is near the horizon, and so as the sun dips toward the edge of the world, the sky around it blooms into a delicate, ethereal blue. It is one of the most counterintuitive and genuinely beautiful things in the solar system. The Curiosity rover has photographed these sunsets, and even through a camera sensor, they are breathtaking. To stand there and see one with human eyes would be something else entirely. The landscape stretches out in front of you, and it is vast in a way that is hard to process. There are no trees, no buildings, no telephone poles, none of the visual anchors we use unconsciously to judge scale. Just rock and dust and the curve of a smaller world's horizon, closer than Earth's because the planet is only about half the diameter. The rocks are everywhere, scattered across the surface in the chaotic way that billions of years of impact, cratering, and volcanic activity and ancient flooding and erosion leave behind. Some of them are familiar-looking, basaltic volcanic rocks, not so different from what you might find near a Hawaiian lava field. Others are strangers, rounded, smoothed, shaped by processes that are still being worked out. The ground beneath your boots is not soft. It is not the fine powder some people imagine. In most regions, it is a mixture of fine dust and coarser gritite material and rocks of varying sizes, and depending on where you are, the surface can be surprisingly firm. But that dust, that fine, pervasive, rust-colored dust, is everywhere. It coats everything it touches. And it is more than just an inconvenience. Martian dust is chemically reactive in ways that Earth dust simply is not. The Martian surface is rich in perchlorates, oxidizing compounds that, if inhaled or ingested in sufficient quantities, are toxic to humans. They interfere with thyroid function. They are present in the soil at concentrations that would be considered hazardous by any environmental standard on Earth. This means that dust getting inside the habitat, inside the suits, anywhere near the crew's biological systems, is not just a maintenance headache. It is a genuine health risk that has to be managed constantly, with dedicated airlock systems, cleaning protocols, and suit designs that minimize the amount of dust that gets tracked inside. Then there is the temperature. The average surface temperature on Mars is around -60 degrees Celsius, colder than anywhere permanently inhabited on Earth, but that average hides a dramatic daily swing. Near the equator, on a clear summer day, temperatures can climb to somewhere around 20 degrees Celsius in the early afternoon, briefly, tantalizingly close to a mild spring day in the mid-latitudes of Earth. And then the sun sets, and within hours the temperature has plummeted to -70, -80, -90. The thin atmosphere simply cannot hold heat the way Earth's can. It bleeds away into space almost instantly after sunset. A human being caught outside in a failing suit during a Martian night would not survive long. The pressure outside your suit is about 600 pascals, less than 1% of the atmospheric pressure at sea level on Earth. Your suit is not just keeping you warm, it is the only thing between you and a near vacuum. Without it, the moisture on the surface of your eyes would begin to evaporate. The gases dissolved in your blood would start to bubble. You would lose consciousness in seconds and be dead in minutes. The suit is not equipment. It is a portable life support system that you are entirely dependent on every single time you step outside, and it has to work every time, with no exceptions. And yet, despite all of that, despite the cold and the dust and the toxic soil and the near vacuum and the radiation, astronauts would still go outside. Because the surface of Mars is one of the most scientifically extraordinary places in the solar system, and the whole point of sending human beings rather than robots is that humans can do things no robot can. A trained geologist standing in front of an interesting rock formation can assess it, chip at it, smell it, make intuitive judgments about it, collect targeted samples in a way that would take a rover weeks to approximate. Human hands and human eyes and human curiosity are irreplaceable scientific instruments, and on Mars, they would be pointed at questions that have been waiting for billions of years to be asked. The geology of Mars is a record of catastrophic change. We know from orbital observations and rover data that Mars was once a radically different world. Roughly 3 to 4 billion years ago, in what geologists call the Noachian period, Mars had liquid water on its surface, not puddles, not temporary trickles, but rivers, lakes, and quite possibly an ocean covering a significant portion of the northern lowlands. The evidence is overwhelming and comes from multiple independent lines of inquiry. There are ancient river valley networks etched into the southern highlands. carved by flowing water over long periods of time. There are lake sediment deposits in craters, layer upon layer of fine material that could only have settled out of standing water. There are minerals, clays, carbonates, sulfates that only form in the presence of liquid water. Perseverance is right now exploring the floor of Jezero crater, which was almost certainly a lake roughly 3.5 billion years ago, fed by a river delta clearly visible from orbit. That river delta is one of the most exciting places in the solar system. On Earth, river deltas are extraordinarily good at trapping and preserving organic material, the chemical building blocks of life, and sometimes life itself in fossilized form. Jezero's delta is built from the same kind of sedimentary material. It sat at the bottom of a lake for potentially millions of years. If life ever existed on Mars, microbial life, the simple single-celled kind that dominated Earth for the first 2 billion years of its history. A lake bed fed by a river delta is exactly where you would go looking for traces of it. Perseverance has been collecting samples, carefully, methodically, drilling cores from the most promising rocks and sealing them in titanium tubes for eventual return to Earth. The Mars Sample Return Mission, a joint effort between NASA and the European Space Agency, is designed to retrieve those samples and bring them back for analysis in terrestrial laboratories, where scientists can apply techniques far beyond what any rover can carry. The timeline for that mission has faced challenges and delays, and the full plan is still being worked out, but the samples exist. They are sitting on the Martian surface right now, waiting. A crewed mission would transform this kind of science entirely. Instead of waiting years for a rover to traverse a few kilometers of terrain, a geologist in a suit could cover significant ground in a day. Instead of relying on a robotic arm with limited dexterity, a human could pick up a rock, turn it over, examine its texture and color and structure with trained eyes, and make an immediate decision about whether it is worth analyzing further. The history of fieldwork on Earth tells us how powerful this is. Some of the most important geological discoveries have come from a scientist happening to look in an unexpected direction, noticing something that did not fit the pattern, following an instinct that no algorithm would have flagged. Now, about that question, the one underneath everything, was there ever life on Mars? The honest answer is that we do not know, and anyone who tells you they do know in either direction is overstating what the evidence currently supports. What we can say with confidence is this: Mars had liquid water for extended periods during a time when life was already thriving on Earth. The two planets formed from the same raw materials in the same neighborhood of the solar system at the same time. The chemistry of life, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, is present on Mars. The energy sources that early life on Earth used, including chemical gradients and possibly sunlight in the distant past, were available on early Mars. The conditions that we currently understand as necessary for life as we know it were present. That does not mean life arose. The origin of life is still one of the deepest unsolved problems in all of science. We do not fully understand how it happened on Earth, let alone whether it happened elsewhere. But the possibility is real, scientifically serious, and supported by our understanding of chemistry and planetary history. And the implications, if traces of ancient Martian life were ever found, would be staggering in a way that is genuinely difficult to overstate. Think about it this way. If we find evidence that life arose independently on Mars, separately from Earth, through its own chemical pathway, that tells us something revolutionary about the universe. It tells us that life is not a miraculous one-time accident on one lucky planet. It tells us that wherever the conditions are right, wherever there is liquid water and chemical energy and time, life tends to emerge. It tells us that the universe is, in the most profound sense, alive, that we are not alone, not just in the vague hoping sense, but in the deep data-supported, scientifically verified sense. Finding a single Martian fossil, a single ancient microbial mat, a single biosignature preserved in 3-billion-year-old lake sediment would be one of the most transformative discoveries in the history of human knowledge. And finding nothing, finding that Mars, despite all its early promise, despite the water and the chemistry and the time, never produced life, would be almost equally profound, because it would suggest that the step from chemistry to biology is genuinely rare, that something happened on Earth that does not happen easily, and that we might be more alone in the cosmos than we want to believe. Both outcomes matter. Both would reshape our understanding of ourselves and our place in this enormous, ancient, bewildering universe. There is something else worth mentioning here, something that the current generation of Mars researchers thinks about a great deal. The question of life on Mars is not only historical. There is a real, if small, possibility that Mars harbors microbial life today, not on the surface, which is blasted by ultraviolet radiation and soaked in oxidizing perchlorates and thoroughly inhospitable, but underground. Deep underground, where liquid water might still exist, kept liquid by geothermal heat, shielded from radiation by kilometers of rock. Some of the same kinds of environments where we find life on Earth in the most extreme places, deep in the crust in hydrothermal systems, in briny pockets where nothing should be able to survive but something does anyway. Those environments might exist on Mars right now, beneath our feet. The European Space Agency's Mars Express orbiter has reported radar data suggesting the possible presence of liquid water beneath the southern polar ice cap, though those findings are actively debated and alternative explanations involving other materials have been proposed. The science is unsettled, but the conversation is real, and it has a practical implication that mission planners take extremely seriously. If there is life on Mars, even microbial, even ancient, we have an enormous responsibility not to contaminate it. Bringing Earth organisms to Mars, where they might outcompete or destroy a native biosphere before we have even had a chance to study it, would be one of the greatest scientific catastrophes imaginable. International protocols on planetary protection exist for exactly this reason. Every Mars mission carries strict requirements about sterilizing spacecraft before launch. A crewed mission vastly complicates this because human beings are walking ecosystems. We carry trillions of microorganisms in and on our bodies, and no amount of cleaning is going to make an astronaut sterile. This is a genuine ethical and scientific tension that the Mars mission planning community is actively wrestling with, and there are no easy answers. We are not just explorers heading to an empty stage. We are potentially heading to someone else's home, and we should step carefully. But here is what I want you to hold on to from all of this. Here is the thing that gets me personally every time I think about it too carefully. The rocks that Perseverance is drilling right now, the sediment layers at the bottom of Jezero crater that might hold traces of ancient life, those rocks were laid down 3.5 billion years ago. The universe was 2/3 of its current age. The sun was younger and more active. Earth was a world of shallow seas and simple cells, and something was happening on Mars, water flowing, chemistry churning, conditions hovering at the edge of what we call habitable. Something was almost possible, or perhaps actually happening, on that distant rust-colored world, and now, billions of years later, descendants of that early Earth life, creatures complex enough to build telescopes and rockets and rovers, have sent their mechanical eyes to look at those ancient rocks. And soon, if everything goes as planned, they will send their own hands. We are the universe looking at itself. We are the cosmos becoming curious about its own history. And the question we are asking, whispered across billions of miles and billions of years, is one of the oldest and most human questions of all. Let us talk about a Tuesday, not a launch day, not a landing day, not a day where history is being made in any obvious or dramatic sense. Just a Tuesday, roughly 4 months into the surface mission. The dust has settled, literally and figuratively. The initial adrenaline of arrival has long faded. The crew knows the habitat the way you know your own apartment. Every corner, every sound, every smell. They know which panel rattles slightly when the heating system cycles on. They know which crewmate hums while working and which one goes completely silent under stress. They know the Martian day, called a sol, lasts 24 hours and 37 minutes, and that small extra 37 minutes adds up over weeks and months in ways that quietly, persistently desynchronize your body from any Earth-based rhythm you were ever used to. This is what daily life on Mars looks like. Not the highlight reel. The Tuesday, the habitat is small by any standard of comfortable living. Current mission concepts for a crude Mars surface habitat envision something roughly cylindrical, perhaps inflatable to maximize interior volume while minimizing the mass that had to be launched from Earth. The total pressurized volume available per crew member, the actual livable space, would be comparable to a small studio apartment shared with equipment, life support systems, scientific instruments, medical supplies, and 5 other people who you have now been living with continuously for the better part of 2 years. Personal privacy is extremely limited, noise carries, smells carry, every interpersonal dynamic, every quirk and habit and mood is amplified by the enforced closeness in a way that even the most carefully selected and trained crew will find challenging. The air inside the habitat is manufactured. Oxygen is generated through electrolysis, splitting water molecules using electrical power from the solar panels or nuclear reactor on the surface, or extracted from the carbon dioxide in the Martian atmosphere using technology similar to the MOXIE experiment that flew on Perseverance. MOXIE, which stands for Mars Oxygen in Situ Resource Utilization Experiment, successfully produced oxygen from Martian atmospheric carbon dioxide during its demonstrations on the surface, a genuine milestone and a proof of concept for the kind of life support that a crewed mission would depend on at scale. Water comes from recycling, every drop of moisture exhaled, every bead of sweat processed and purified and returned to the system. The recycling efficiency on the ISS has reached above 90%, and Mars systems would need to be even better because resupply from Earth is simply not an option. Food is a more complicated story. A Mars mission would carry the bulk of its food supply from Earth, carefully formulated, calorie-dense, nutritionally complete, shelf-stable for years. The psychological importance of food in isolated environments is well documented and taken seriously by mission planners. Variety matters. The ability to occasionally choose what you eat, to have something that tastes different from yesterday, sounds trivial until you have been eating from the same limited menu for months, and the sameness of every meal starts to weigh on you in ways that are hard to explain to someone who has never experienced real, prolonged monotony. Some mission concepts include small hydroponic growing systems, the ability to cultivate fresh greens, herbs, small vegetables, not primarily for caloric contribution, which would be modest, but for the psychological benefit of growing something living, tending to it, and eventually eating something that was not sealed in a pouch 2 years ago on another planet. The work itself is relentless. EVAs, walks outside on the surface, are among the most demanding activities in terms of physical and cognitive effort. Suiting up alone takes hours of careful preparation. The suit has to be inspected, every seal verified, every system checked. Once outside, the crew operates under time constraints set by the suit's life support capacity, oxygen supply, battery life, thermal management. They are working in bulky, pressurized gloves that reduce manual dexterity significantly. in a suit that is itself a pressurized vessel pushing back against every movement they make. Field geologists who have tested Mars analog suits in environments like the Canadian Arctic or the Arizona desert consistently report that simple tasks, picking up a rock, taking a photograph, using a geological tool, take 2 or 3 times longer in a suit than they would with bare hands. Every EVA is a carefully choreographed operation with specific objectives, contingency plans, and a crewmate monitoring from inside the habitat who can provide guidance and call an abort if anything looks wrong. And between EVAs, there is an enormous amount of work that happens inside. Sample processing, data analysis, equipment maintenance, medical monitoring, communication with mission control. That 20-minute each-way delay means that the crew essentially operates autonomously on a day-to-day basis, making their own decisions and reporting results rather than asking permission. This is a fundamental shift from how human spaceflight has operated historically, where mission control has had a detailed and immediate role in decision-making. On Mars, the crew is the primary authority. They have been trained for this. They have protocols for this. But the weight of that responsibility, compounded with everything else they are carrying, is real. The Martian sky becomes familiar in ways that are strange to contemplate. You learn the sun's path across that butterscotch sky. You learn the dust devils that spiral across the plains on warm afternoons, genuine whirlwinds, sometimes hundreds of meters tall, photographed many times by rovers and visible from the surface as spinning columns of rust-colored dust tracking across the landscape. You learn the 2 moons, Phobos and Deimos, both tiny, both lumpy, both nothing like Earth's moon. Phobos is so close to Mars and orbiting so fast that it rises in the west and sets in the east, moving visibly across the sky over the course of a few hours. Deimos is so small and so distant it barely looks like more than a bright star. On a clear night, both are visible simultaneously. It is wrong in a way that never quite stops being wrong. No matter how long you are there, the nights are extraordinary in a different way entirely. The Martian atmosphere is so thin and so relatively dust-free after a calm day that the night sky is almost preternaturally clear. The stars are sharper than they ever look from Earth's surface, blazing with a steadiness that is almost unsettling. No atmospheric turbulence to make them twinkle, just hard points of ancient light in every direction. The Milky Way arches overhead in a band of cold fire, and somewhere in that sky, if you know where to look, and you absolutely know where to look, because you have memorized it, because it is the first thing you searched for on your first night, there is a blue-white point of light that is home. It is moving, slowly, imperceptibly to a casual glance, but moving, both Earth and its companion moon, orbiting the sun, the pair of them visible as a double point on the best nights. And here is the thing about that moment, the thing that every psychologist who has studied long-duration spaceflight and isolation will tell you is the most emotionally loaded experience a Mars crew would face. It is not dramatic, it is not a crisis. It is just a Tuesday night, and you are standing on the surface of another world, looking at a point of light, and that point of light contains every person you have ever loved, every city you have ever walked through, every ocean, every mountain, every piece of music that ever moved you, every conversation that ever changed you, all of it compressed to a single pixel in an alien sky. The overview effect that astronauts describe from the ISS, that profound shift in perspective, that sense of Earth's fragility and beauty and wholeness, would hit differently from Mars. On the ISS, Earth fills a significant portion of your view. It is massive, immediate, overwhelmingly present. From Mars, Earth is a point of light, and that distance, that visual reduction of your entire world to something so small, would demand a different kind of reckoning, not the ISS astronauts' awe at Earth's beauty. Something quieter, something that goes further down. Researchers who study Antarctic winter over cruise The closest analog we have on Earth to Mars surface isolation, consistently find that the relationship with home becomes deeply complex over time. Early in the mission, the pull of home is a source of motivation and comfort. Later, it can become a source of pain. Letters and messages from family that describe ordinary life, a child's school play, a birthday dinner, a neighbor's new dog, can feel impossibly distant, impossibly unreachable, in a way that the early mission's excitement had insulated against. The technical term researchers use is asthenia, a generalized fatigue and emotional blunting that can develop in prolonged isolation. Mission psychologists actively monitor for it. The countermeasures are imperfect, and yet, the crew would also have something that no Antarctic researcher has ever had. They would have Mars right outside the door, an entire world to explore, a world that no human eyes have ever seen in person before, a world that holds 3.5 billion years of geological and possibly biological history in its rocks and dust. Every EVA is a walk through deep time. Every sample collected is a piece of a story that predates the existence of complex life on Earth. The privilege of being there, the sheer, staggering, unrepeatable privilege, would be something the crew would feel every single day, and it would sustain them in ways that no amount of psychological preparation or virtual reality distraction can replicate. There is a word that comes up repeatedly when astronauts and researchers talk about what makes long-duration spaceflight meaningful. The word is purpose. The crews that fare best psychologically are not the ones who are the most extroverted or the most resilient in isolation by conventional measures. They are the ones who have the deepest sense of purpose, who understand why they are there, who feel genuinely connected to a mission that is larger than themselves, who believe that what they are doing matters. And on a Mars mission, the purpose is not abstract, it is not a metaphor. You are on another planet, the work is real, the stakes are real, the history being made is real. That sense of meaning is one of the most powerful forces in human psychology. It is in many ways what makes us capable of extraordinary things. Viktor Frankl, the psychiatrist and Holocaust survivor who wrote about human meaning and endurance in the most extreme circumstances imaginable, argued that the human being can bear almost any how as long as they have a why. The Mars crew would have a why that is among the most profound any human being has ever had. They are not just enduring, they are pioneering. Now everything we have talked about, the radiation, the landing, the surface life, the science, the psychological weight of distance, all of it has been building towards something, because there comes a day, after a year or more on the surface, when the launch window back to Earth opens, when the planets align again and the mathematics of interplanetary travel says now. And that day arrives with a complexity of emotions that is genuinely difficult to untangle. Relief, terror, grief, anticipation, because going home means leaving Mars behind. It means climbing back into a spacecraft and trusting again the engineering and the physics and the human ingenuity that got you there. It means another 7 months of deep space transit, more radiation, more bone loss, more isolation. And it means that when you finally step back onto Earth, if you step back onto Earth, you will be a different person than the one who left. Changed in ways that nobody fully understands yet, because nobody has ever done this before. The journey home and what awaits at the end of it is where this story ends. And let's bring everything together, the launch off Mars, the return through deep space, and what it would actually mean for humanity when these explorers come back. What it would mean for our species, for our understanding of who we are and what we are capable of when human beings stand in front of a camera somewhere on Earth and say simply, "We went, we were there, we came back." The day the crew leaves Mars is not what you would expect. There is no crowd, no countdown broadcast to billions of people, no cameras on the ground capturing the moment from dramatic angles. There is just the crew, The habitat, the rust-colored plains stretching out in every direction, and a spacecraft that has been sitting on the Martian surface for over a year, waiting. They have spent the previous days doing final checks, loading samples, securing equipment, running through every procedure on the departure list with the same methodical care they have brought to everything since the moment they left Earth. And somewhere in the middle of all of that practical, necessary work, each of them has found a quiet moment to go to a window or step outside one last time and look, because they know something that no human being who comes after them will ever quite know the same way. They know what it is to be first, to stand somewhere that no member of their species had ever stood before, to look at a landscape that human eyes were seeing for the first time in the history of life on Earth. That is not something you set down and walk away from easily. That is something you carry for the rest of your life, whether you want to or not. The launch off Mars is a different engineering problem than the launch off Earth, and in some ways a more elegant one. Mars has roughly 38% of Earth's surface gravity, and its atmosphere is so thin it offers almost no aerodynamic resistance. You do not need the monstrous multi-thousand-ton launch vehicle that was required to escape Earth. A much smaller Ascent-10 vehicle can do the job, carrying the crew from the surface to Mars orbit, where the main Earth return spacecraft has been waiting, either left there during the initial arrival or sent ahead unmanned in preparation. The ascent vehicle burns its engines, the ground falls away, and in minutes rather than the many long minutes of an Earth launch, the crew is in orbit above a world they will probably never see again, because here is something worth sitting with. The first people to go to Mars will almost certainly not be the last. If the mission succeeds, if they come home safely, and the data and the samples and the human testimony of what is possible comes flooding back into the scientific and engineering community, the next mission will be planned before the first one has even landed. Mars, once reached, does not become less interesting, it becomes more interesting. Every answer it gives us generates 10 new questions. Every discovery reshapes the map of what we do not yet understand. The first crew to stand on Mars will have opened a door that humanity will walk through again and again with growing confidence and growing capability, until the idea of human beings on Mars is no more exotic than the idea of human beings in Antarctica. But that is the future. Right now, the crew is in Mars orbit, and the trans-Earth injection burn, the engine firing that will send them back across the void, is coming. When it happens, it is quieter than the departure from Earth was. There is no roaring crowd of engines, no max Q, no plasma sheath, just a sustained burn that shifts the trajectory, that tips the spacecraft out of Martian orbit and onto the long curving path back home. And then once again silence, once again the stars, once again the days and weeks and months of deep space transit. But this transit is different. On the way to Mars, the crew was moving toward the unknown. Every day brought them closer to something they had never experienced, never seen, could only imagine. There was anxiety in that, but there was also the forward pull of anticipation, of curiosity, of the mission not yet accomplished. On the way home, the dynamic shifts. They have done the thing. They have been there. The mission, in its primary sense, is complete. And now there are 7 more months of weightlessness, of radiation, of the same small spacecraft, of the same faces and voices, except now there is no grand unknown waiting at the end. There is home. Familiar, beautiful, longed for home. And the psychological research on return journeys in isolated environments suggests, perhaps counterintuitively, that this phase can be harder than the outbound leg. The goal is visible but still impossibly far. The gap between where you are and where you want to be is measured not in miles but in months, and every day can feel like it is not moving fast enough. The crew would also be returning with bodies that have been through something unprecedented. The accumulated radiation exposure, the bone and muscle loss, the cardiovascular changes, the possible subtle effects on cognition and vision, all of it will need to be assessed, monitored, and treated over months and possibly years of rehabilitation. Scott Kelly spent a year on the ISS and needed significant recovery time after returning to Earth's full gravity. A Mars crew would have been in space for roughly 14 months of transit time alone, plus however long they spent on the Martian surface under 38% gravity, which is better than nothing, but still not the full gravitational loading the human body evolved under. Walking on Earth again, carrying their own full weight for the first time in years, will be an experience that is both joyful and physically demanding in ways their bodies are not immediately ready for. There will also be something harder to quantify, something that the psychological literature on returning explorers hints at, but cannot fully capture in data. The experience of having been somewhere so remote, so alien, so profoundly separate from ordinary human life, and then returning to a world that has continued on without you, that has changed in small and large ways while you were gone, that is full of people who understand what you did intellectually but cannot possibly understand it experientially. That transition is genuinely difficult. Astronauts returning from the ISS have spoken about it. Antarctic expeditioners have written about it. There is a word some researchers use, re-entry shock, that refers not to atmospheric physics, but to the psychological disorientation of returning to normal life after an extreme experience. For a Mars crew, this would be amplified by an order of magnitude. They went to another planet. They walked on it. They looked for signs of ancient life in 3.5 billion-year-old lake sediments. They watched the sun set blue over a frozen alien desert. They saw Earth as a point of light. No debrief, no support group, no amount of professional psychological care can fully bridge the gap between that experience and standing in a grocery store trying to decide between two kinds of cereal. The world will feel both overwhelmingly beautiful and slightly unreal. The ordinary will seem simultaneously precious and impossibly small, and yet humans adapt. We are almost embarrassingly good at adapting. The same cognitive flexibility that allows our species to thrive in environments from the Arctic to the tropics, from sea level to high altitude, from hunter-gatherer bands to modern cities, that flexibility will work on returning Mars explorers too, slowly, incompletely, with rough edges that may never fully smooth out, but it will work. Because the pull of connection, of belonging, of the people and places and small rituals that make up a human life, that pull is stronger than almost anything. Now let us step back, all the way back. Because I want to end this story not in a recovery facility, or a debriefing room or a grocery store, but somewhere wider, somewhere that does justice to what all of this actually means. 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity. The center of that cloud ignited into a star, our sun. The leftover material formed a disk, and in that disk, small grains of dust and ice began to clump together, colliding and sticking, and growing over millions of years into the planets of our solar system. One of those planets formed in what we now call the habitable zone, the distance from the sun where liquid water can exist on a surface. On that planet, roughly 3.5 billion years ago, in the warm, shallow chemistry of early oceans and hydrothermal vents, something happened that remains the deepest mystery in all of science. Chemistry became biology. Molecules that could copy themselves began to copy themselves. Life began. From that beginning, from those first microscopic, fragile, unremarkable-looking cells in a primordial sea, everything followed. The first photosynthetic organisms that filled the atmosphere with oxygen, the first complex cells, the first multicellular life, the first animals, the first vertebrates crawling onto land, the dinosaurs, the small mammals that survived the asteroid impact 66 million years ago, the primates, the hominids, us. And now, after 4.5 billion years of that process, after all of that improbable, magnificent, unbroken chain of life, one of the products of that chain has figured out how to leave, how to build machines powerful enough to escape the gravity of the world that made them, how to travel through the void between planets, how to land on another world and walk around on it and ask questions about it and bring pieces of it home. Think about that chain for a moment. Every ancestor you have ever had, going back to the very beginning of life on Earth, lived and died on this planet. Every generation, every individual, every species in the entire history of terrestrial life has been confined to this one pale blue dot, until now, until this generation, until the people who are right now designing the rockets and the habitats and the life support systems that will carry human beings to Mars for the first time. We are, right now, at one of those hinge moments in the history of life on Earth. The kind of moment that, if you could somehow show it to any of our ancestors, any of the countless generations of humans who looked up at Mars and wondered what it was, would seem like a miracle, not because it is supernatural, but because it is the product of something that is in its own way just as astonishing as anything supernatural could be. It is the product of curiosity, of the persistent, irrepressible, deeply human refusal to look at a question and say that is too hard, or that is too far, or that is not worth knowing. The universe is roughly 13.8 billion years old. For most of that time, it was dark, not literally, not without stars and galaxies and the light of nuclear fusion blazing across the cosmos, but dark in a particular sense. Dark in the sense of being unobserved, of containing unimaginable complexity and beauty and violence and deep time with no mind present to register any of it. And then, on at least one small rocky planet, orbiting one ordinary star on the outskirts of one spiral galaxy among hundreds of billions, something changed. Eyes opened, minds formed, questions began. We are the universe's way of knowing itself. We are the cosmos become conscious, looking back at its own history with wonder and trying to understand how it all happened. And the journey to Mars is part of that looking. It is part of the same impulse that led the first humans to draw animals on cave walls and count the movements of the stars and ask why the sky is blue and what the stars are made of and whether we are alone. It is the same impulse, scaled up, pointed outward, given rocket engines and radiation shielding and sample collection tubes. Carl Sagan wrote that we are a way for the cosmos to know itself, that our science, our art, our love, our longing, all of it is the universe experiencing itself through us. And when those first astronauts step onto the surface of Mars, they will be carrying with them every question that humanity has ever asked about that world. Every child who ever looked up at the night sky and asked what that reddish light was. Every astronomer who ever mapped its surface through a telescope. Every engineer who ever spent a sleepless night debugging a guidance system. Every scientist who ever bent over a microscope looking at an extremophile from a deep-sea vent and thought maybe they will all be there, in a sense, standing in that butterscotch light, looking out over that ancient, frozen, extraordinary world. We are made of stardust, literally, not metaphorically. The carbon in your body, the iron in your blood, the calcium in your bones. These elements were forged in the cores of stars that lived and died before our sun was born. When those stars exploded as supernovae, they scattered their materials across the galaxy, and some of that material found its way into the cloud that became our solar system, our sun, our Earth and us. We are the universe looking at itself with the very atoms the universe made. And Mars, that rust-colored world sitting in the next orbit out, is made of the same stuff. It is kin in the deepest sense of the word. Going to Mars is not leaving home. Not really. It is expanding our understanding of where home begins and ends, And here is what I want to leave you with. The journey we have walked through together in this video, the launch, the radiation, the months in deep space, the terror of landing, the dust and the cold, and the extraordinary science and the longing for home and the return, all of it is not a story about technology. Technology is just the means. The story is about something older than any rocket, older than any telescope, older than any civilization. It is about the part of us that looks at the horizon and cannot help but wonder what is on the other side. The part of us that asks questions we do not yet have the tools to answer. The part of us that sends our fragile bodies and our vast curiosity out into the dark, not because it is easy or safe or comfortable, but because that is who we are. That is what we do. The first humans to walk on Mars have not been born yet, or perhaps they are children right now, looking up at the night sky from a backyard somewhere, feeling that pull without yet having a name for it. They will face challenges we have not anticipated, solve problems we have not imagined, and experience things that will take years to fully translate into words. But they will go, because we'll send them, because we will build what needs to be built and solve what needs to be solved and fund what needs to be funded and learn what needs to be learned, generation by generation, failure by failure, breakthrough by breakthrough, because that is the story of our species, and it is far from over. The cosmos is vast, the questions are deep, and we are just getting started.